all set, I suppose. Well, thank you very, very, very much for the invitation. Some of you might be worried. Okay, so this is going to be mathematicians speaking about maths, so we won't understand anything. Okay. A few comments on that. First of all, it's going to be a really non-technical talk. There will be very little math. That's not a proof, because every time I hear one of my colleagues, mathematicians, saying, well, this is a very general and simple talk, usually I'm lost after 3 minutes. I don't understand a word. So really, there should be very, very little math in this talk. Well, maybe so that you relax a little bit, I have very famous quotes that I like to recall. One is this quote, which is, well, people say that Goethe was the one who said it first. I've mentioned this quote so many times, but I still like it very much. Well, anyway, it goes like that. Mathematicians are like French people. Whenever you tell them something, they immediately translate it in their own language, and it becomes impossible to understand. So I'm a French mathematician. Well, there is another quote that I like very much also, which was by a rather nationalistic Russian writer, which at the end of the 19th century said that only French people can explain what they don't understand. And, well, I'm not sure about explaining, about not understanding, that comes very easily to me. But anyway, and final quote from my hero, Johnny von Neumann, who said once, one never understands mathematics, one gets used to it. So if you feel that you don't understand mathematics, don't worry, you're not the only one, and most of the time I'm in the same situation. So I think I understand what could be the difficulty. So instead of beginning with the first, I'm going to take some chances with the presentation. So instead of continuing the talk, let me stop it. And let me show you a video. Okay? I'm trying. I will try. Which clearly won't look like any kind of math. I just want to put it on full screen. Okay, I did it. Okay, no comment. So let me leave you. I'll be back in 40 minutes. Okay, so you see what's happening. It's a traffic intersection. The place is irrelevant. It's, of course, to make it fun, the speed has been increased a little bit. But you see that what should be a total disaster, in the end, it works. And from time to time, okay, that's bad shape. No. People strategize, find solutions. That seems like a bad shape. No. No way. It works. Okay? So the address where you can find all kinds of funny videos is funmansion.be. I'm not being sponsored by them, let me make, but at least you can find lots of funny videos there, and at least you will have learned one thing during my lecture, which is a good web address. But anyway, so why did I show you this, this video? Because what this video shows, okay, now we are going to see if it works. Well, perfect. In fact, I'm not the one who discovered this video. This video was shown to us by engineers that are working with us in the context of those so-called mean-field games. And those engineers are from a Chinese telecommunications giant, namely Huawei. And they are subsidizing our research. It's public sponsoring. So we publish what we do with them and so on. And they showed us this video because they said, you know, the next mobile telecommunication networks are going to look much more like an intersection like that than, you know, with intersection with traffic lights and so on. What's the point? The point is decentralized intelligence versus centralized intelligence. And if you think about the future mobile communication networks, one expects very soon to have about 2 million connected objects per square kilometers, and there is no way you can have some kind of centralized intelligence that organize all the traffic, okay? So centralized intelligence, I mean, that's something I always think, that's a Frenchman speaking, is that typically, you know, you take this intersection, we have a saying in France that if you put a cop in the middle of the intersection, it gets all stuck. Traffic won't move again. I mean, so you may argue whether this really means centralized intelligence or not, but anyway, you can't have someone directing traffic and it's not going to work. Okay, so we still have no clue what I'm talking about, right? Min-field games, okay. So the goal is to introduce, well, sorry, I should have said that before. This is an ongoing joint project that we began more than 10 years ago, something like, well, about 12 years ago, even more than that, with my friend, colleague, collaborator, Jean-Michel Lasserie. Jean-Michel Lasserie is a strange beast. He is a part-time mathematician. He doesn't, for about 20 or 30 years, he didn't have a position in academic circles. He was working in companies. But the guy has always been a very, very imaginative guy. Well, anyway. Okay, so the goal is to create and to use, to analyze mathematical models for situations and not solutions involving many agents and players. So we started this, we introduced this new class of models for the average, and average is related to what in statistics and in statistical mechanics and statistical physics is known as mean-field theories. So the average behavior of small agents, so agents, players, game theory. So a mixture of statistical physics ideas and game theory. We started that in the early 2000s. And why did we start that? Well, we started because we had another big operation which was being sponsored by two major companies in France. One is called EDF, that's the French electricity company, and the other is the so-called Green Bank, which is Crédit Agricole. And the title was Finance and Sustainable Development, how to use economical/financial tools in order to improve the sustainability of economics. So it was a huge field. We started very early. People were not talking about green finance in the early 2000s and so on. So we really had no clue where to start, what to study, and so on. And then progressively, the subject got organized. Now it's even fashionable. But in the meantime, we realized that if you think about social issues, you have three characteristics: long-term planning, strategy, lots of externalities, or if you want, many players. Okay? And there's a third one that I will comment later on. Clearly, this is not something that you can address by classical game theory, because classical game theory, if you, as soon as you have more than a few players, it's, you cannot track. You cannot do much with classical game theory. So what I'm going to show you very briefly with a very, very simple presentation has lots of applications, of course, to economics, finance, social networks, crowd motions, telecommunications, meaningful data, big data, or artificial intelligence, and so on. Well, maybe let me stop the lecture again. I mentioned crowd motion. In fact, I realized about 1 or 2 years ago that a group of engineers in charge of building one of those huge towers tallest. Everybody claimed that it's going to be the tallest tower in Qatar. They were using min-field games to understand how people would evacuate a floor. In most public buildings, whenever you build something now, you have also to consider the possibility of evacuation, and you have to produce in many countries a numerical simulation showing how the room is going to be evacuated. So there are commercial software which consider that people are like fluid particles. And now with min-field games, we have other options which consider people as being intelligent people that can strategize. Okay, so let me show you a very simple, no shock, influence of congestion, common shock. Okay. So what are we looking at? This is just a tiny numerical simulation, no fancy colors, no nothing. So typically what you have there, let me try to use this. So think of this as being, well, it's a room like that. So what you have are people sitting in rows like that, and there are the exits are on, let's say, on this side. Okay. So I have not yet defined min-field games, but min-field games allow to produce simulation of that type. So clearly you see the number reducing, so it's going fast, but I don't want to slow down. Let me show it once more. And I will come back later on to explain what is the modeling assumptions which are behind that. So you have those obstacles, and people are just exiting in a symmetric way. But you realize that there is something wrong in this modeling. Something is missing. So typically what you expect, if you have any experience of people getting out, is that there will be like, groups, clusters of people forming at the end of the rows. So, so what we realize is that we had not taken into account what is called congestion. Okay, so the fact here, in some sense, all points, independently of the density of people in those locations, were treated in a similar way. So now, if you say that a higher density you cannot move as freely as you can in other places, then that's you need to add another term in the modeling. And here is the simulation that when you add this term, I will get there eventually. Okay, so now that looks better. You have those peaks at the end of the rows and, exiting. Fine. So you have some kind of numerical simulation that shows in a reasonable way how people are exiting. Well, then you can make the situation even more complex. And that's where strategy becomes more natural. You may say that there are two potential exits, but only one is going to be open and you don't know which. Okay? What happens? Well, if you have a fluid, this question doesn't even make sense, right? Because fluid particles, there is no information for them. We don't know which one is going to be open, okay? So essentially you see no difference when you change the rule of the game with any kind of those simulations. In particular, there is no anticipation. So while here, let me show you, this is just a very, very simple example. I hope I picked up the right one. I can't see anything. Okay, so people anticipate in a symmetric fashion, no big deal. So everybody is massing near the exit, and then suddenly we realize that the door on the right is the one open. So it's a very simple example of a situation that involves, and I'll come back to that later on, that involves a random event, because which door is going to be open is randomly selected, a random event that affects everybody. So I will insist a lot on common noise, common random effects against independent random effects. There's going to be a large populations, like particles. So in physics, we are used to have independent noises from one particle to the other. If you think about, between quotes, real-life situations, very often there are random events, and we all are submitted to the same random event. So that's a major difference. And this creates some difficulties, mathematical difficulties, as we'll see later on. So it's time that I start explaining a little bit what I mean by min-field games. Well, maybe. But I want to certainly to mention that there was also some independent introduction of a very particular class by Wang, Keynes, and Malame, some engineers in 2006. Okay, I'm not sure. Can you see the green spot? Not quite, huh? Here, do you see? Well, anyway. I want to mention that people in economics have been thinking about very particular cases of min-field games for quite a while, so-called anonymous games, which are discrete time games. I've been very much impressed by this classical work in macroeconomics by Krussell and Smith. I didn't know this, we are not aware of this work, but visiting quite often Chicago, the University of Chicago, and very often I've given talks in economics. I know very well Bob Lucas, who's one of the big guys in economics in Chicago, and Bob was a Nobel Prize winner in economics some years ago. And I remember very well, after telling him this story about min-field games, he told me, well, that's cool, there should be lots of applications. But you know, there is this paper by Krussell Smith, we never understood it. I'm sure it's a min-field game. Can you explain it to us? And in fact, this is an amazing paper where those two guys invent, so they don't write any kind of mathematical model. They don't write any kind of equation, but they are mentioning, you know, the population of players, and they give the rules for the game, and then they do numerics, which mix Monte Carlo simulations with an approximation of measures of the space of the set of probability measures, and in fact, without any equation, the numerics, the numerical procedure is correct for the problem. After a few years of work, we were able to make sense and answer Bob Lucas' question. So it's a research community expansion, and of course, in mathematics, there is probably one international congress meeting on min-field games every 3 months. In economics, finance, telecommunications, energy, and many other things. It has also become quite fashionable, so that's why I had lots of fun to see in a paper which was about Olympic sailing, okay? Olympic sailing, it was a paper which was some kind of review paper about all kinds of mathematical / engineering / fluid mechanics and some mechanical, etc. approaches to Olympic sailing. Fine, a very serious paper. And the last section was devoted to you know, really navigating. And not so much the mechanics, but the strategy for Olympic sailing. So they were mentioning, of course, game theory, and I really laughed when I saw in the paper that maybe one should use min-field game because that's a hot topic in game theory. I said, well, that's a sign that indeed it has become a fashion, because there is no way min-field games can explain anything about Olympic sailing. So, I mean, part of the fashion is that also people tend to use it in crazy ways. So one has to be serious in terms of applications. As I mentioned before, it's a combination of min-field theories, which are classical in physics and mechanics, and the notion of Nash equilibria. So here's the third factor I didn't mention, is that we are interested in situations where you have lots of players, and we're interested in situations where all those players, we assume that they behave in a rational way. So rational is a very dangerous word. We don't know what that means, really. The notion I'm using here is that each player is indeed trying to optimize something, okay? So that's what rationality is. So mimicry, herd behavior, can be rational, because this means that I'm trying to have the same type of behavior than the others and the neighbors and so on. Okay, so that's considered with this vocabulary as rational. Okay, so let's go on. An example, I already did that. So let me begin with a very, very simple example, which is not new. And if you're worried about the mathematical notations, let's keep in mind the following example. We are going to the beach, and we have to decide where to put our towel. Okay? That's a very simple question. In fact, that's, in some sense, a dual problem, a classical problem by Otterling in economics, which is about ice cream carts. Suppose that you own an ice cream cart, you go to the beach, where are you going to put your ice cream cart? It looks like a silly question, but think about, where do I want to put a new antenna for a mobile communication network? Where do I want to open a new store? Okay, it's exactly the same problem. Okay, so let's go back. Here, I suppose that the ice cream carts are already on the beach, so they are points of interest. Being French, points of interest means places where you can eat and drink, right? So you have a restaurant, ice cream carts, and you want to be not too far away from those places. Okay, so that's a question that you want to ask. Where am I going to put my towel on the beach? Fine. Of course, what I'm going to do is not to teach you where to put your towel. You know how to solve that. And my point is, what those models try to do is to say that if we all decide in a rational fashion about where we're going to put our towels, what is going to be the resulting distribution of towels? Can we predict the outcome? Okay? It's not about teaching anyone. This is a very simple position game. And so each player, you have n player, has to choose a position in a given set on the beach. According to a criterion, he's trying to minimize a certain criterion, like the distance to the place of interest, to the restaurant, and possibly something else. But this criterion will depend on the others. So typically, the example I will mention is whether I want to be in a crowded place or an uncrowded place. So I want to be close to a restaurant, but very often I don't want to be in too crowded a place. Okay? So this depends on the others. So I have n criteria, n players, and each player would like to minimize, but it depends on the others, and you cannot minimize simultaneously. You cannot find a minimum of n functionals simultaneously. Okay, so that's why Nash, the famous mathematician, who got the Nobel Prize in economics for a 2-page paper, which proposed the notion of Nash equilibria. It's a very simple notion that I'm trying to recall here. So a Nash equilibrium is a set of points denoted with upper bars, x1 bar, xn bar, such that whenever you freeze all the others, except the ice one, then the xi bar guy should be the minimum of the resulting functional where all the other guys have been frozen. This is an equilibrium. It's like a fixed point situation because all the others are being fixed in order to define the xi guy. But of course, this guy is going to be fixed for the determination of the others, the other location of the equilibrium. So this is a very natural notion, notion of equilibrium, but it's plagued with lots of difficulties, like non-existence, but much more severe is non-uniqueness, and all kinds of absurd equilibria and instabilities and so on. So difficult to manipulate without trying to select more. Question is, and that's the main question I will address very quickly and very simply, is when we let the number of players go to infinity, why does it get simpler and why does it become simpler? Okay? Exactly as if we take classical mechanics, n-body problems can be very difficult. But if you let n go to infinity, you have continuum mechanics. Let's take the air in that room. Okay, so suppose that we want to understand how the air moves, what is the temperature of the air in that room. So if we go down to the molecules and the electronic motions, we are doomed. Okay? But on the other hand, we have macroscopic models called the heat equation, Navier-Stokes equations, that do a pretty good job to predict what's going on. So it's exactly the same type of hope we were entertaining when we started working on that, is that somehow letting the number of agents go to infinity might simplify the situation by erasing all kinds of discrete, finite grain irregularities. Okay? Of course, you need then assumptions, like in mechanics. If all the particles that you are looking at before going into, let's say, a macroscopic equation or a kinetic model, if all the particles are different, you cannot say anything. So here you have, there is a similar kind of assumption, is that you have to say that the agents, the players, are indistinguishable. Doesn't mean that they're identical. It just means that they're indistinguishable. Of course, we may have several populations, in which case you have an extension of what I'm mentioning here, and that's not something that I'll describe now. What I want to explain is how we let n go to infinity, because mathematically there is a problem. It's a stupid problem, but it's a severe problem, is that we are dealing with the state space, the bits to the power n location. So for each n, the mathematical setting changes. So in order to have a fixed background, there is this idea that in some sense, when you have symmetric functions, what you're really looking at are functions over probability densities, probabilities. And the reduction is that instead of looking at points, you look at what is known in statistics as the empirical measure. Okay? So you forget points, and here comes measures, probability measures. So this is a change of point of view. I will come back to it later on. When you do that, you realize, and there is, I mean, for years I've developed in my courses at Collège de France all the mathematical theories behind this passage from a space to the power n quotiented by symmetries to the set of probability measures and analysis and differential calculus and PDEs. You don't want to know that. Well, I mean, if you really want to have more details on min-field games, there are a bunch of books that have been out, in particular books by Carmona and Delarue, Springer. It's 1,500 pages long, and it contains about 30% of the mathematical theory. There is also my series of lectures at Collège de France that you can download. So beware, I taught about this subject for about 4 years. So it's 4 times 18 hours. Okay, you can download all of this. So don't, okay, unless you have to. Unless, you know, it's either death penalty or that. But anyway, so don't, but unless, well, there is only one case where you might want to download it, is when you have difficulties sleeping at night. Then I guarantee that 5 minutes of any of those lectures and you will be sleeping like a baby. Okay. Anyway, so more seriously, if you want to find material, you can find it there. So Nash equilibria converge to something which is a min-field game where the unknown is really the density of towels on the beach. And the way you, it's a Nash equilibrium in that sense, is that you take a generic player. Well, what is a generic player? It's just a point, a position, or the position of a generic player. It's just a point in the support of the measure, because outside the support, the measure is 0, there is no one. Okay? And this, as a Nash equilibrium, you fix all the others. Fixing all the others, if you neglect, as it is a case of automatically here, the self-interaction, as we would say in physics, then what you're left with is you fix all the others, and you want to say that this x is the minimum point of this function. So you see this is like a complicated fixed point problem, because you're looking for a measure such all the points in the support are minima of a function that depends on that measures, okay? It's an absolutely non-standard minimization problem, and that's for the simplest problem you can think of. So it turns out that there are general existence and stability results, that you have uniqueness when f is monotone. Well, okay, so let's give a more specific example. So here is the example, that's a line, that's a beach. Here is f of xi, like the distance to a restaurant, okay? Distance, let's say, to the square. If I'm nearby, that's fine. If I'm far away, it's very hot and it's very tiring. And then I want to incorporate a term which model the fact that I may want to be in a place which is not too crowded. So typically there is a length. If you think about towels, it's a few meters, and let's say a dozen of meters, and you want to compute, and you're looking at a number of points which fall in that neighborhood, and it also depends on n, on epsilon. Okay, so whatever. So when g is increasing, this means that you are averse to crowds. You're trying to minimize. You don't want to be in a place where there are many people around. Okay, so normal people tend to avoid crowded places. Of course, G may be also non-decreasing, which means that you like crowds, abnormal people, okay? Well, they have another name, those abnormal people. They are called teenagers. Okay, so anyway, G is decreasing. In terms of functions of a measure, that's the type of object you have. This is mathematical. I don't want to waste time about it. As in Boltzmann theories, when you let epsilon go to 0, what you have is this kind of minimization problem. And what you prove, what the general mathematical theories tell you, is that when G is increasing, you have a unique distribution. Okay? Fine. While if G is decreasing, you have non-uniqueness in general, and that's natural. Think about it. Decreasing means that you want to be with other people, right? So suppose you have two places of equal interest, and everybody wants to be with, with lots of people. So everybody will flock to one place or to the other. You have two solutions. So clearly, you see that there is a dissymmetry with respect to attraction or not. So in some sense, it's also reminiscent of, classical statistical physics a posteriori. General structure, and then I'll conclude with a few perspectives and so on. So don't look at that. And this is, okay, there are no children in the assistance. So no nightmares tonight. Okay, so this is really, just to give you one simple example of what the equations really look like for min-field games. So this is the so-called master equation in a very simple, well, in a very particular case. So here's the list of assumptions which are behind that case. Okay, some of you might be familiar with something which is very important in decision theory, which is called the Bellman equation, dynamic programming. This is a major tool in decision making, it's a major tool in engineering, a major tool in control theory. So it's a principle, and so you have many types of Bellman equations depending on the settings you're interested in. Min-field games is exactly the same thing. In some sense, it's the next step, involving not a single agent, but a crowd of small agents, okay? So it involves a certain value function that depends on x. What is x? Well, that's a collection of variables you're using to describe the state of a player, okay? So it may be phi, it may be discrete, it may be continuous, it may be age, height, wealth, whatever. It depends on the problem, okay? On the beach example, it was a position. On the example of the crowd, it was position. If we are talking about mobile telecommunication, it may be position, it may be power, it may be the bit rate that has been, the number of bits that have been transmitted. So X depends on the model. What is M? Well, M is a global state of the population. Okay, so you have now a function that depends on X, the variables of the agents that you are using to describe the agent, and the total distribution of the population, which is an infinite dimensional object, which is a priority measure. So this ugly-looking equation is an infinite dimensional nonlinear partial differential equation. So it's a partial differential equation on the space of priority measures. So that's absolutely frightening. And in fact, Russell Smith couldn't really write in their economics paper a partial differential equation, because if they had written something, it would look like a little bit like this equation, and there was no way. Okay, I don't have time to, there are two situations where this infinite dimensional problem reduces to finite dimensional problems, which are of course much more tractable numerically. It's a case where you only have independent noises, and the other case is when you have finite state space. So typically you have agents that are on graphs, living on graphs. So that's why there is a very strong connection that I don't have time to discuss with machine learning, artificial intelligence, and meaningful data. Let me just mention at that point that we, about 8 years ago, we had a startup company called MFG Labs, which in 3 years went from 1 person to 50, and we sold it to a big ad company, and but that's another story. But that was, of course, related to crowds on finite state spaces. I want to mention this particular case, which is about independent noises, and I will conclude with a simple example, which I believe is a fun example. So what you have here is that a reduction to a system of partial differential equation. I don't want to describe it. It looks like nonlinear heat equation, like the equation that modeled the heat and the temperature in that room, except that one is going forward in time and the other is going backward in time. How come? This I want to emphasize it because the evolution of the population is going forward in time. It's following the dynamics of a population. So that's the M equation. That's the evolution of the... that's okay. So that's the M equation. That's the lower equation. It's following the evolution of the equation of the population. So typically, if we're interested in kinetic model heat equations, which are all mean-field equations for particles, we would have only this equation going forward in time. It's combined with a decision-making equation, which of course is forward-looking. So it's going backwards. Choosing is about anticipation, okay? Planning, it's about making strategy is always about anticipation. If you don't anticipate, it's just a blind, blind reaction. You just observe where you are and you have a strategy. As soon as you do any kind of planning, any kind of strategy, you anticipate. So it has to be backward. And you have systems of a nature which clearly is new, because people are used for PDF partial differential equations or ordinary differential equations of thinking of equations going forward in time, because we are just following the natural arrow of time. And in decision making, that's the Bellman equations, we go naturally backward in time. And here we have both at the same time. So this explains why automatically it's rather new, and why it has been so much fun in math, because that was empty. There was nothing. Yeah, I think that's more than enough. Okay, okay, so functions of many variables. Well, maybe I can say that one of the explanations is that when you have u that depends on x1, xn, which is symmetric in x1 and xn, it's really what you think is that you have a function of the space of probability measures, or equivalently, and all those are very important to exploit, to analyze the so-called master equation, which is this infinite dimensional nonlinear partial differential equations. You can also think that you have a functions of random variables whose law is m. In the case of a finite dimensional space, think that Those are just random variables which takes values, those position xi with priority 1 over n. So you have various equivalent ways to insert the initial problem with n players in a setting which is independent of n, and the first one is important for what is known as compactness, and the second one is important because that's a flat geometry. I don't want to go there, that's too technical, sorry for those comments. There are many, many questions. Well, okay, so those are the new facts about optimal stopping, intertemporal preference rate, how you can go from those min-field games to models which are very popular, agent-based models, kinetic models. Also min-field games with a major player, min-field games with Bayesian learning, and so on. So there is much more to be said. Let me conclude 1 minute with what I call an S example. Okay, S certainly for simple, but also S for silly, stupid. Okay, so let me conclude with a stupid example. This example, which will show how one uses this box, this mathematical toolbox, which is called min-field games. It's a so-called, I mean, Americans call it a Mexican wave. In France, we call it the Ola. You know what that is? What is the Ola, the Mexican wave? Good. Okay, so indeed, this in the stadium. People go to a stadium and create this wave. It's called the Mexican wave because it started during the soccer, I mean, football World Cup in Mexico. So, and that was the first time it was done in the stadium. There is a huge scientific literature on the Ola, on the Mexican wave. Well, you may say, if you are skeptical, you may say there is a huge scientific literature about any subject. That's true. But still, why is that the case? Well, it's a very interesting example of synchronization. People use big words like theory of emergence and so on. And I should say that there are connections with agent-based models, and there are groups of physicists also that have begun to work on min-field games because of fishes and birds and so on. Anyway, so there is this whole scientific concern about synchronization, about creation of regular objects like this wave propagating out of chaos and so on. Okay. So there is a huge scientific literature about the Ola, and there has been experiments. It turns out that the Ola always turns clockwise in all countries, in both hemispheres. I remember asking a friend of mine from Argentina, does the Ola in Argentina go the same direction? He told me first, no. I said, oh my God, I mean, northern, southern hemisphere, clockwise, anti-clockwise. I mean, I was immediately thinking about crazy things. Following day, he came back and told me, no, it goes always clockwise. Okay, so during the Olympic Games in Sydney, they made an experiment of creating a Ola going anti-clockwise. It went perfectly and at exactly the same speed than the Ola, the usual Ola. Ola, one should say that the speed of the Ola has been measured very, very carefully, and it's always the same worldwide, essentially. And of course, all the stadiums have roughly the same size, okay? So there is regularity. So trying to make some kind of models out of this regularity. We don't care about the Ola. That was a fun example. We were more interested in synchronizations about, propagations of crises of certain events and so on. But the Mexican wave was a good example. So let me tell you another experiment that I like very much. Of course, when you see this wave, you immediately think, if you have been scientifically trained, you immediately think about solitons, those solitary waves that propagate along a channel and that may interact with each other, and which after a period of interactions essentially resume their propagation as if nothing had happened, maybe slightly modified, but as if nothing had happened. So those are solitons, solitary waves, and so on. So physicists had this very natural idea, let's see if they are solitons or not. So how do you do that? You have to make two waves collide. So they ran an experiment in the Netherlands, in a stadium. So you had two aulas going in front of each other. It was a complete disaster, okay? Nothing happened. Yeah, of course, I mean, those are not food particles, they are people. Can you imagine the guy sitting in the middle and he's there and he's seeing two waves coming on him? What am I going to do? Oh, yeah, that's exactly what happened, okay? So I'm emphasizing the fact that people anticipate. So how do we use our model, which is only one explanation? We don't need formulas. Let's discuss a few assumptions. We're going to say that, well, typically in a stadium you have about 100 rows, okay? So we are going to take a column and say that this is the population on the column is huge. So 100 is not really huge, but that's an approximation, okay? So we're going to have a density on that column, which is being parameterized by the angles. Let's say the stadium is a circle. Fine. What is the variable of each agent, each person in that column? Well, that's the position. Z equals Z between 0 and 1. Z equals 0 means sitting. Z equals 1 means standing. Z between 0 and 1 means being like that, okay? Cost function terms. Clearly, moving kinetic energy is part of the cost. Also position, Z equals 0, Z equals 1 is comfortable, but in between, that's highly uncomfortable. So you have clearly a cost function which is concave, right? Second term. Third term, I want to be in the same state than my neighbors. Mimicry, okay? So you have two parameters. So let's fix the first one, which is the ratio between comfort and kinetic energy. And let's think about the last parameter, which is this parameter, which says how much I want to be in the same position than my neighbors. Then you immediately have a system of equation automatically because of Mansfield games, and you can start to do numerics and to do the mathematical analysis. So you do the mathematical analysis and you prove the following statement. That's a fun exercise, which says that if the mimicry coefficient is not too small, you have up to a change of orientation, you have a unique stable periodic wave. You have infinitely many stable periodic waves, but only one which is stable. Lowest frequency, if you want, okay? So that's a prediction which in particular says that it should be if the dimensions are the same everywhere, if the Earth behavior is the same everywhere, you're going to always have the same speed. So I'm not saying that's the simplest way to make a model for the Euler, but that's at least an explanation. So that's, I wanted to conclude with this example to introduce you to this fun area, which is quite new. I think in mathematics, most people have not even yet realized that all this was taking place in other communities and so on. In economics, it's being taught now in many universities. It's moving in computer science and communication networks. It's beginning. But I would say that if you're an engineer and if you're familiar with decision-making engineering, that's a very natural tool to have, which creates, because of its very structure, lots of interesting mathematical problems which are essentially open, and that's always fun. So I guess that independently of the advertisement for my child, which is Mansfield Games, the point that I want to make is certainly how much fun it can be to do some kind of mathematical series, and how much fun I have when I see connections with real life problems and real life applications. By this, I do not mean that fundamental questions are not fun. That's lots of fun. And if we are mathematicians, let's face it, that's when we do series that we have the most fun. But the possibility of seeing in your lifetime the type of things you're doing really being applied is lots of fun. So let me conclude by thanking one person that I don't think thank enough, which is the taxpayer in France, which essentially has paid taxes, allowing me to have fun for 40 plus years, and having a semi-decent salary and doing exactly what I want, namely having fun. Well, let me hope that you will have as much fun as we are having, as I'm having. Thank you very much.